In this video, we're going to talk about solving and graphing inequalities. And the term inequality refers to the fact that there are no equal signs in these expressions. Here you could see a greater than or equal sign, here a less than, here a greater than, but no equal sign. So that's where that term comes from, inequalities. So here in red, we have a relatively simple inequality. So to solve this, we would simply subtract 2 from both sides, and we would end up with x is greater than or equal to positive 3. So to graph this, we would go to our number line. I always like to put 0 as a reference point. We would identify positive 3, and we would put a closed circle here because of the fact that this is greater than or equal to. And at this point, what I like to do is put a little miniature x on both sides of that colored in circle. And then I go back to the simplified form and I say to myself, it says x is greater than or equal to 3. So I come back to my number line and I ask myself, which of these two x's is in a region where the x would be greater than or equal to positive 3? And that would be this side. So then I discard the other x and I go ahead and I shave the area to the right of this positive 3 and I place an arrow sign. So again, this was a relatively simple inequality, solving and graphing. But in this video, I'm going to focus on what you see in blue. And these are called compound inequalities. And compound inequalities mandate that you solve two separate inequalities. And then you have to take into account whether you want to graph an AND problem versus an OR problem. And throughout this video, this is the type of problem that we are going to deal with. Shown here are some typical compound inequality problems that you might see at your homework. And by the end of this video, you're going to be very comfortable solving both this portion of the compound inequality as well as the other portion and graphing the results, taking into account that they are looking for an OR graph. Here, same thing. We're going to show you how to solve for R in both circumstances and then graph it to depict the term AND. I want you to notice something here. See how they have negative 7n minus 12 in the middle? Folks, this is an AND problem because what this is saying is that negative 7n minus 12 is greater than or equal to negative 33 and negative 7n minus 12 is less than negative 26. Now, it turns out something very interesting. When you are dealing with an AND problem, the graph most often is going to look like this, a dumbbell. When you're dealing with an OR problem, it's going to look like this, two arrows going in different directions. So this is the way I like to think about this. Okay, here are some problems that have been solved on this worksheet. So let's take a look at this. Okay, let's deal with the OR problems first. Okay, so here we have an OR problem. Look at the solution set. You have a space in the middle with an arrow going in one direction and another arrow going in the other direction. To me, this looks like a boat with oars, spelled O-A-R, extending in either direction. Okay, here again, there's a gentleman here in this boat, and there's two oars, one in this direction, one in the other direction. Look at these other OR problems. Here's another one. When you solve for x here or that, you have two oars, as in boat oars, going in different directions. One last one, an OR problem with two arrows going in different directions, simulating a boat oar. Now, let's look at some AND problems, and let's get some graph intuition. And we see here that this is an and problem right here. And look, it looks like a dumbbell. You have two circles, either closed or open, with shading in between, just like this blue and pink dumbbell. Okay, I told you before on the previous slide that when you have an expression in the middle between two constants, this is an and problem in disguise, because p over 2 has to be greater than or equal to -3, and p over 2 has to be less than 0. Look at the solution. Looks just like a dumbbell. Okay, here's another and problem up here. Look, another dumbbell. Two circles with shading in the middle. So I suggest, folks, that you take a screenshot of this, because the vast majority of and problems are going to look like a dumbbell, and the vast majority of or problems are going to look like two oars going in different directions. Now, it's very important to recognize that that is not always the case. Okay, so here I have some problems and solutions. Okay, let's make this a little bigger. Okay, up here in the upper right, we have an or problem with two oars, two arrows going in different directions. This is typical. But look at number 16. Here we have an and problem, yet there is no solution, so no dumbbell. Here we have an and problem, but no dumbbell. Rather, we just have a single open circle with one arrow. Here, number 19, this is atypical. It's an or problem, but we only have one arrow pointing. And finally, number 20, here's an or problem, and it's all real numbers. So what I'm going to do in this video is I'm going to show you when you have a typical and or, like here. Here's an and with a dumbbell. That is typical. Here's an or with double arrows. Typical. However, I'm going to show you when to look out for the atypical solution. And I'm going to give you the intuition as to which way the graph is going to go. Typical format with an or and arrows in two directions, or an and with a dumbbell, or atypical when you have an and problem and no dumbbell. Let's now spend a few moments talking about the number line. So here in purple we have a typical number line, and as you know, a number line consists of negative integers, 0, as well as positive integers. Recall that integers are counting numbers, no fractions, no decimals, positive, negative, as well as 0. Now on the right side of the number line, here in the positive area, it's very clear to us that 6 is greater than 5, or 5 is greater than 3. However, there is some confusion on this side of the number line. So it's important to recognize that when you're looking at a number line, when you're comparing two numbers, the number to the right is always greater than the number to the left. Okay, so in other words, -1 is greater than -6 because it sits to the right. Okay, let me show you on my drawing here. So if we're at -1 versus -6, because -1 is to the right of -6, -1 is greater. A lot of students think it has to do with the fact that -1 is closer to 0. That is not the case. Okay, for example, if you look at -1, which is very close to 0, versus +6, +6 is greater than -1 because it sits to the right. So when you look at a number line, when you're trying to compare two numbers, which is greater, the one on the right is always larger. Let's look at a hypothetical where rather than give you actual integer values, I just gave you letters, and I asked you which value is greater, B, which corresponds to this position on the number line, or A? The answer would be B. B would have a higher value than A because B sits to the right. Similarly, if I gave you two letters on this side of the number line, C and D, and I asked you which of these had a higher value, you would tell me D is greater than C because D is situated to the right of C. Whatever is to the right has a higher value. Whatever is to the left has a lower value. Okay, so you might want to remember it that way. Left is lower value. Let's now review how to solve an inequality, and we're going to pay particular attention as to under what circumstance we need to flip the sign. In other words, as you can see, in this blue inequality, we start off as a less than or equal to. However, there are some circumstances where we end up flipping this sign as we solve for the variable v. So let's go ahead and solve this blue inequality. The first thing I would do here is I would add 4v to both sides. That would cancel this out. And that would leave me with 9v plus 10 is less than or equal to negative 17. So far, I have not multiplied or divided by a negative. Those are the two circumstances where we need to flip the sign. Multiply or divide by a negative. So far, in fact, we've done addition only. No need to flip the sign. Next move here for me would be to subtract 10 on both sides. That would cancel these out. And I would be left with 9v is less than or equal to negative 27. Again, no impetus to change the direction of that sign. Finally, my move would be to divide both sides by 9 in an attempt to isolate the variable. Final result would be v is less than or equal to negative 3. Now, you might say, well, wait a minute, we have a negative answer. Why didn't we flip the sign? Well, the reason is we didn't divide or multiply by a negative. Our last move was to divide by a positive. So no need to flip the sign in this blue inequality. This is our final answer. Okay, let's now move to the yellow inequality and see where solution of this inequality leads us. Okay, so here my first move would be to subtract 2p from both sides, canceling these out. And that would leave me with 2p plus 20 is less than 14. No need to flip the sign. We did not divide or multiply by a negative. My next move here would be to subtract 20 from both sides, leaving me with 2p is less than negative 6. Now we would divide by 2. Final answer would be p is less than negative 3. So far, absolutely no reason to flip the sign. Now let's look at this inequality. We have negative 10a plus 3 is greater than 4. So my first move here would be to subtract 3 from both sides. We would have negative 10a is greater than 1. And next I would divide by negative 10. And as soon as I divide by a negative number, that means I'm going to have to flip the sign. So my final answer is going to be a is less than negative 1/10. Flip the sign whenever you divide or multiply by a negative number in the pursuit of isolating the variable. Let's now move on to solving and graphing some inequalities. So in this first one, we have b is less than 4. This is already solved for us. How do we know that? Because our variable, in this case b, has no neighbors and no negative sign. So when we have this scenario, we can proceed right to the number line to graph it. I always like to put a 0 for reference. And the next thing I do is I go to the number in question. So here we're at positive 4. And because that is a less than sign only as opposed to less than or equal, I put an open circle at the number in question. The next thing I do is I put a small b on either side of that circle. Okay, both sides, whether it's a colored in or closed circle or open, I put the variable in miniature form on both sides. Now I come back to the problem and I literally read it out loud or in my head. They want the region where b is less than 4. So that's going to be this miniature b. b is to the left of 4. That means this b is less than 4. So I'm going to go ahead and shade the area that corresponds to that b. Okay? And if you want, you can go back and discard the other one to avoid any confusion. Okay, let's look at this next one. This is solved for us. I understand there's a negative sign over here, but if you look at the variable itself, it has no neighbors and no negative signs. This means we can proceed directly to the number line. So let's do that. Let's put our number line, 0 for reference. We go to -4, but this time we used a closed circle because this is less than or equal to. Okay, we put a little miniature k on both sides of that, in this case, closed circle. We go back to our problem. They're looking for the region where k is less than -4. That's going to be this region. This is the region where k is less than -4. Why? Because k is to the left of -4. So now we can discard the other k, and that's our final answer. Okay, in this next one, we have to do a little bit of work. This is not solved for x. Look, it has a neighbor. So how do we get rid of that neighbor? We subtract 7 on both sides. These cancel out, and that gives us x is greater than 3. Now we can go to our number line. 0 as a reference. We go to +3. We have an open circle because of the fact that that is a less than sign as opposed to less than or equal. We put a miniature x on both sides of the circle. Then we go back to the problem. They're looking for x greater than 3. Which of these x's is greater than 3? The answer is the one on the right. That is where we shade. And then we discard this one. Next one. Again, not quite solved for the variable. We have a neighbor. What's happening between the neighbor and the variable? Multiplication. Because there's multiplication going on, we do the opposite operation, which in this case is division, and we end up with z is less than or equal to +2. Notice, we did not flip the sign because we are dividing by a positive number. We have now solved for z. We are ready to go to our number line. We go to +2. Because this is a less than or equal to sign, we use a closed circle. We put a little miniature z on either side of that closed circle. Then we go back to the problem. They want to know where z is less than or equal to 2. That's going to be this z right there. So we're going to shade this way, and we're going to disregard this z. Next one. Here, again, we have to do a little bit of work. Not solved for x. We have 2 neighbors. In this scenario, where you have 2 neighbors, it is always easier to get rid of the one that's being added or subtracted first. This neighbor is in tight with the x. That's how I think of it. This one is easier to pick off at first. So let's get rid of this one by subtracting 2 to both sides. That's going to bring us to -6x is greater than or equal to 12. Now, to get rid of that negative 6, we would divide both sides by negative 6. The minute or the second we find ourselves dividing by a negative in the process of solving for x, we know we're going to have to flip the sign. So let's just go ahead and do it right away. So now we're going to have x is less than or equal to negative 2. Okay, let's see if I have some room right underneath here. Okay, we don't. So I'm going to go up here in this upper corner. Here's my number line. We're graphing x is less than or equal to negative 2. We go to negative 2, and because it's less than or equal, it's going to be a colored in circle. So here's negative 2, and there's our colored in circle. We're going to put an x on either side of that negative 2, and then we're going to go back to our problem. They want to know where x is less than negative 2. Where is x going to be less than negative 2? It's going to be this way. And then we disregard the x. This is where you're going to see the words and or. If we have an and problem, typically we're going to get a dumbbell. You're going to have two circles. One or both might be colored in, shading in between them. With an or problem, it's typically one arrow going this way, the other arrow going that way, like oars coming from a boat. Let's start with the first one. Okay, here we have an and problem, therefore we're going to expect dumbbells, or a dumbbell. We are not yet solved for x. Look, x has a neighbor. How do we get rid of that neighbor? We do the opposite operation, which in this case is to add 6 to both sides, and we get x is less than 11. Notice, we did not flip the sign. Let's go to the next one. Here, we're going to add 4 to both sides. That cancels this out, and we're going to have x is greater than or equal to 6. Okay, so I want you to notice two things, folks. In solving for x for both of these expressions, there was no flip of the sign. And secondly, we have a variable less than something, in this case 11, and the variable greater than something. So I'm going to put greater than something and less than something. Okay, you'll see why in a moment why I'm doing that. Okay, so two things. No flip, the variable's less than 11, and the same variable is greater than 6. When we have this scenario, it's typically going to be a dumbbell with an and problem. So let's graph each of these separately. Let's go to positive 11 first. Because this is only a less than sign, as opposed to less than or equal, we're going to have an open circle. Next, I'm going to ask myself, they're looking for the areas where x is less than 11. So I'm going to put an x on both sides of that open circle. And I'm going to ask myself, which of these x's fit this criteria? Which of these two x's is less than 11? It is none other than this one. So I'm going to go ahead and I'm going to eliminate that x, discard it. Now I'm going to shade the region that includes that x. But because this is an and problem, and because I'm expecting a dumbbell situation, I'm not going to go crazy with this arrow and do it all the way to the left. I'm going to stop about right there. Now I'm going to do the other expression. I'm going to go to positive 6. Because this is a greater than or equal sign, I'm going to use a closed circle. I'm going to put a little x on either side of that 6. Let's use a different color. I'm going to go back to my problem. They're looking for the region where x is greater than 6. Which of these two x's is greater than 6? The answer is that one. So I'm going to discard the other x, and I'm going to shade the region that contains that x. Notice, we have a dumbbell. There was an and problem, no flip of the signs. We had the variable less than something and the variable greater than something. Let's move on to our next compound inequality, and this is an OR problem. So unless we see something atypical, we're going to expect two arrows going in different directions, just like oars in a boat, something like that. Okay, so here we go. Let's solve this side. Add 1 to both sides, and this cancels out. We have c greater than or equal to positive 8. Over here, we're going to subtract 3 from both sides, and we're going to have z is less than negative 4. Okay, so notice two things. No flip of the sign, and we have the variable greater than something, and we have the variable less than another number. So no surprises. Let's go to positive 8. Let's put a closed circle because this is z is greater than or equal to 8. We're going to put miniature z's on both sides of that 8. We're going to go back to the problem. They're looking for the region where z is greater than or equal to 8. Which of these z's is greater than or equal to 8? It is this one. So we're going to discard the other z, and we are going to shade this way. That's our first arrow. Next maneuver, we go to negative 4. Because that is only a less than sign, we're going to make that an open circle. We're going to put a miniature z on both sides of that open circle. We're going to go back to the simplified expression. They're looking for the region where z is less than negative 4. Which of these z's is less than negative 4? Remember, the one to the left is always less. Therefore, it is that z that is less than negative 4. We discard the other one, and we shade the region that contains the correct miniature z. So look, we have an OR problem, and we have what looks like two oars coming from a boat. Arrows going in two different directions. And that's because everything was normal. There was no flip of the sign, and we had the variable greater than something, and we had the variable less than something. Let's go to the next one. Okay, let me give myself a little more room here. I apologize for this delay. And let's move this up a little. Okay, good. Okay, we have an AND problem. So unless we have a surprise, we're going to expect a dumbbell. Let's solve each of them. We're going to subtract 2 from both sides. These cancel out. We're going to have n is less than or equal to negative 7. Over here, we're going to subtract 6 from both sides. And we're going to get n is greater than or equal to negative 12. We had no flip of the sign. We have a variable that is less than something, or less than or equal, and we have the same variable that's greater than something. No surprises, we're going to expect a dumbbell. Let's go to the first one. Let's go to negative 7. Because it's a greater than or equal, less than or equal to sign, we're going to color it in. We're going to put miniature n's on both sides of the circle. We're going to come back to our problem. They're looking for the region where n is less than negative 7. Which of these two n's is less than negative 7? It's this one. So we're going to remove the one that is not involved, and we're going to shade, but we're not going to go crazy with a long arrow because we expect a dumbbell. Now we go to the other one, negative 12. Because it's a greater than or equal to sign, we're going to do a closed circle. We're going to put a miniature n. Let's use a different color so we're not confused. A miniature n on both sides of that circle. They're looking for the region where n is greater than negative 12. Which of these two n's is greater than negative 12? It's going to be this one. So we discard the other one, and we're going to shade the region that contains that n. But notice, we don't keep going. We have to stop here. That's because it's an and problem. We have to satisfy both criteria. So if we extend this blue line here and include everything here, this is not the correct solution because it doesn't satisfy both criteria. Look, if we extended that blue arrow, that would mean 0 is part of our solution set. Is 0 less than negative 7? No. 0 is greater than negative 7 because 0 sits to the right of negative 7. So that extended blue arrow does not fly. You have to satisfy both criteria. We have a dumbbell situation because we have no surprises. There was no flip, and our variable is less than something, and our same variable is greater than something else. Here, folks, we have an and problem. Whenever you see a complex like this, this is an and problem. They're saying that this middle segment, 3p plus 7, has to be both greater than negative 5 and less than or equal to 22. So I prefer to separate them and do two separate problems. Okay, let's do the first one. First thing I would do here is I would subtract 7 from both sides, and I would get 3p is greater than negative 12. Divide both sides by 3, and I would get p is greater than negative 4. No flip of the sign. Next one, subtract 7. 3p is less than or equal to 15. Divide both sides by 3. P is less than or equal to 5. Okay, now notice what we have here. We have had no flip of the sign, and we have a variable greater than a number and the same variable less than a number. So we have both greater than and less than. So I expect this to be a typical and problem. There's no surprises here. I'm expecting a dumbbell. So let's look at this first expression. We go to negative 4. We use an open circle. We put little miniature p's on either side of the circle. They're looking for the region where p is greater than negative 4. Which of these p's is greater than negative 4? It's this one. Why? Because it sits to the right. Discard the other one, and we shade. Okay, we don't go all the way off the chart, off the screen, because we know this is an and problem. And and problems are typically dumbbell problems, which means there's two circles with shading in between. Okay, let's go to the next one. This is a closed circle because you have a greater than or equal to sign. We're going to put miniature p's on either side of that closed circle. They're looking for the region where p is less than or equal to 5. Which of these two miniature p's is less than 5? It is this one. We're going to discard the other one, and we're going to shade the region that includes that p. There's our final answer, a dumbbell. There was no flip of the sign. Our variable ended up being less than our variable was greater than something, and the same variable was less than something. In this next problem, we have an OR situation. That means, unless there's a surprise, we're going to see two arrows going in different directions. Let's proceed to solve this. First thing I would do on this left expression, I would subtract 5 from both sides. And I would get negative y is greater than or equal to 4. We have not yet solved for that variable because there's a negative sign. So we have to divide both sides by -1, and because we are dividing by a negative, we're going to flip the sign. And we're going to get y is less than or equal to -4. So we have a flip. Okay. Next one, opposite side I should say. We're going to subtract 4 from both sides, cancel this out. And we're going to have 3y is less than -9. We're going to divide both sides by 3. And we're going to end up with y is less than -3. So look what we have. Not only do we have a flip of the sign in this first expression, but here we have y less than a number, and over here y less than a number again. So we do not have our typical situation. We have a flip, and we have less than and less than. We're going to expect something different. So when you have either or both of these criteria, you got to be careful. We are not going to have the typical situation where you have arrows going in opposite directions. So we're going to be very cautious as we do this problem. Let's go to -4 first. Okay, we're at -4. We're going to put a closed circle because this is less than or equal to. Okay, this is -4. We're going to put a miniature y on both sides of that circle. We are then going to ask ourselves, which of these miniature y's fits this description? We're looking for the region where y is less than -4. Which of these miniature y's are less than -4? It's going to be this way, like that. Okay, we're going to discard the other y like that. Okay, now we're going to move over here. And we see that y is less than -3. So we're going to go to -3. We're going to do an open circle. We're going to put another set of miniature y's. We're going to do a different color. And we're going to go back to the problem. They're looking for the region where y is less than -3. That's going to be this y. We're going to discard the other one, and we're going to shade the region that is less than y. So look what we have, folks. We have a unique situation for an OR problem. All of this is going to be shaded. You are more inclusive when you have an OR problem. It's going to be shading here or shading there. You err on the side of being more inclusive when you have an OR problem. So this is your final solution. This is unique. The reason it's unique, what tipped us off, was that we had a flip of the sign, and we had this scenario where the variable was less than something and the same variable was less than something else. That's not usually what we see. In this next compound inequality, we have an and. That means typically we're going to see something like this: a dumbbell with shading in between, unless we see something unique happen as we solve for the variable on both sides. So let's start on the left. First thing I would do here is I would subtract 13 from both sides. So that would give me -4a is greater than or equal to 16. Now I would divide by -4. I immediately have to flip the sign. So I would get a is less than -4. Over here, I would add 14. I would get 6a is greater than 24. I would divide by 6, and that would give me a is greater than 4. Okay, so notice, folks, we had a flip. Okay? That immediately puts me on guard that we are not necessarily going to have a dumbbell situation. What else do we have? We have A is less than something and A is greater than something. Okay, that is what we typically see. So there's nothing unusual than that of that. Okay, A is less than something and A is greater than something. But it is this flip that puts us on notice. Okay, let's go to -4. We're going to put a closed circle at -4 because there's a less than or equal to sign. We're going to put a little miniature A on either side of the circle. We're going to go to the expression. They're looking for a region where A is less than or equal to -4. This miniature A is less than -4. We're going to discard the other one and we're going to shade over here. Okay. Now we're going to go to this side. We're going to go to +4. Because it's only a less than symbol, we're going to keep that open. We're going to put a miniature A with a different color. We're going to go back to the expression. They're looking for the region where A is greater than 4. This A is greater than 4. We're going to discard here and we're going to shade this way. Okay. Folks, look what we have here. It's an AND problem. Therefore, the solution has to satisfy both criteria. There is no way that you can have a value over here and over here. Therefore, this is no solutions. And what tipped us off that this was going to be a unique scenario was the flip of the sign. Whenever you have a flip of the sign, or wherever you have the same over here, where the variable is less than and less than, or greater than and greater than, you'd be on the lookout for a variation where we're not going to see a dumbbell. And sure enough, we don't. We see two arrows going in different directions. And if you have an AND problem, there's nothing that could satisfy being over here and at the same time being over here. It's impossible. Therefore, this is no solution.